Here we go. Right. So most of you, not all of you, are from physics backgrounds, and I think everyone here is from some sort of STEM background. I've seen some chemical engineering, some EECs, etc. But all of you probably have the unifying factor of you want to learn how to do computer programming effectively for your science research. But that's not really trivial. There's literally like an entire major about how to program. So if you're a busy STEM major of some kind and you don't have time to take like the 61 series and operative CS and things like that, then what do you do? Especially because not everything in those classes is relevant at all. So how do you know what you need to know? How do you get the parts you need? How do you start using them and get used to them? Do you just like Google, how do I do science with code? Do you like endlessly bug your CS major friends? Do you take CS classes? And like, that's just way too much in my experience and in other people's experience of like, imagine trying to balance like a full load of physics classes and a CS class as well. Maybe some of you have done that. So we saw like a bunch of these problems in ourselves and like friends and peers. And we were like, well, we should just put together like one semester of all the stuff you need to know for research and like none of the rest or very little of the rest. Like only the stuff you actually need to know in a much lower stress environment than like a CS61B or something like that. So that's our motivation going into it. More specifically, we want to teach you these three things. The first one is computational thinking, which is basically, I've got an idea of how a math thing works. How do I make a computer do that? So that breaks down a bit, and we'll go into that more, into how do I think about something step by step? There's this computation and this computation, and then I have a result that I want to visualize. And there's a lot of like non-trivial things there that you sort of have to train yourself to do. And that Alan and I have somewhat done, train ourselves to do, just from experiencing it a lot.
Yeah. We are not professionals, and neither of us is a CS major, but we are hoping that we've learned enough to transfer a little bit of that knowledge to you guys.
Yeah, I don't think we even necessarily either know everything that's in the class. I don't know much about your section. You don't know that much about mine.
Yeah.
So we're both going to be learning things as we go.
Yeah. I will be learning an entire language with the rest of you. So
nice.
Yeah.
And honestly, I think that's better for this kind of like informal undergrad PNP class. Like, we don't want it to be like, we're so much, we're your age, but we're so much better than you. No, we're not. We've just been doing this a tiny bit longer, if that. Yeah. Okay, so our second big goal is understanding computational coding tools. Like probably some of you have heard, if you've been doing CS for research or a project or something like that, you should parallelize this. Okay, what does that mean? When do I do it? And maybe some of
hardest question.
Yeah. Sometimes you'll have to work on a remote computer that's like somewhere else, especially now that we're all remote due to the pandemic. Some people may have to work on a computer that's like on campus or at LBL or SSL. How do you do that? And maybe sometimes you join a project and their entire code base is in like IDL or something, and you've never seen IDL. No class ever told you you got to be prepared to learn IDL. Like, what even is that? And how do other people do it? So that's the second big block of what we want to get across. The third one is just a collection of best practices. This is a little less like mathematically cool, but it is probably the most important thing in here. Like, you don't want to share, if you're sharing code with someone else, you don't want to do it by like emailing them a file. If you write some code, you want to be sure that someone else picking it up can read it and understand it. And if you're writing code, you want to be sure that you're writing it so that if you want to add features later and things like that, you can do that easily without, you know, rewriting the whole thing and wasting hours and hours. So, you know, a little less like cool, but probably a lot more important. And in fact, if you go into a research position and say, I know how to use Git, which is a version control system, for example, that'll give you a huge leg up for those of you who haven't done research yet. Like, so many of these projects are built on these technologies.
Yeah, it's very difficult to emphasize enough how important understanding like the tools underneath what you're doing is. Like I in research or industry, depending on where you decide to go, I worked at SpaceX this summer, doing some ASIC integration work, which is taking a bunch of components and making a computer chip out of them. But there's a whole lot of complicated tools associated with that. But the thing that my bosses were most happy about was that I understood how to use Git. And Git is a system for storing file, like for keeping track of different versions of your code. And that is the thing they were by far the happiest about. So like understanding the tools underneath what you do is, if you get anything out of this class, that's what we want you to get out of this class.
Yeah, exactly. And we are going to have a lecture on Git about
Yes.
halfway through, like week 7 or something like that. So, we'll get there. So let's go a little more specific on each of those points. Computational thinking. Suppose someone's given you a paper or something like that, and in there they've got this like equation of something is an integral of something else. It doesn't really matter what the variables are. How do you tell a computer to do that? You might break it down into steps like this. I won't bother to read them off, but the idea is there's a lot of like subtleties to how you do it. Like, what x values do you choose? How do you apply f to all of them? Do you like write a loop for that? Then you multiply them all by some dx. What even is dx? Add them all up. And so there's a lot of like non-trivial translations of this math idea to code. And to complicate things even further, maybe someone will say, oh, just call a NumPy function. Okay, what's that? How do I do it? Then you maybe look up the documentation, you get this. And then to me, it's not immediately clear, at least, how I would go about actually doing that to like get this quantity Q that I'm interested in. And then what if some things change later? And does this work fast enough? And there's so many like little subtleties to this idea of I've got a math equation and I want to translate it to code in the best possible way. And so we're going to cover that in quite a bit of detail with a bunch of different use cases. The second one, this is just a bit more detail on the kind of things we were talking about before. Picking up a programming language you've never seen before, working on your own small part of a really big collaboration, which is how a lot of the research groups at Berkeley do it. I'm not entirely sure, but I think Alec can say more about this. I think there's a lot of like particle physics groups that are part of the Atlas collaboration. So you may be working on a massive code base that like thousands of people work on, but you got to only do your little part of it because you don't want to break the rest of it for thousands of people while you're doing that. Of course, you won't even be allowed to break it, but like it's important to understand how that works. And another really important thing is, how do you know when a particular tool is a good fit? If you're just told, compute this thing, okay, what programming language do you use? Do you like request time on a remote computer or not? What package do you use? And there's a lot of little choices in there that we hope we can help you with. And then the third one is best practices. So again, not much use in me just reading off these things, but there's a lot of benefits to organizing your code well. And these are things that aren't really taught elsewhere, like in maybe the Python DeCal or ULab or something like that. They might teach you like, here's how a function works, here's how loops and conditionals work and all that. And those are like important foundations, and it's great that you've got them if you have. And if not, we'll talk about that in a couple of slides. But then on top of that, you need to start like thinking from the top down, sort of. How do you structure really big things so you don't like lose track of what you're doing, so that it's really clear to you or to anyone else? How do you not lose code as you're working on it? How do you share code with others? So again, a lot of learning to be done there. So those are the things that were our goals. Here are the things that we're not necessarily going to focus on. We're not going to focus on the basics of programming. If you want a refresher, I also work on curriculum stuff for ULab, so I can absolutely point you to resources for that or like invite you to some lectures. But mostly, next lecture is going to be Alad talking about like the basic Python tools we need, and we'll be building off that. If you have had like a one semester CS class, like ULab, the Python DeCal 77, anything like that, you should be totally fine. If you haven't, you may also be fine, but the review assignment that we've just released may help you with that. And the review lecture next week may help with that. And if you've got concerns about your preparedness, come talk to us after this and we'll help out.
Yes, and just for clarity, the homework assignment that we just released is a 2-week homework assignment. So if you realize you're a little bit rusty with Python and you go and try to do the first homework and you find out that like haven't done this in a while, it's you know, a little bit difficult, you can wait until the review lecture to start. Although I like also you can start now if you've done a little bit of Python before, like you should pick up everything pretty fast.
Yeah, just take a look at it, see how you feel, talk to us. We are online way too much and way too available, so
Yeah.
we're happy to help with that. We're also not going to talk about domain-specific tools. So for example, CERN root is a really common package, but we're not going to, but when we say research programming, we don't mean like the specific tools. The idea is if we learn like general principles about how good research code works, you can pick up any of the specifics on the spot, like as you need to.
Yeah. And part of that is one of the things we want to get you to be really good at doing is, you know, finding a tool and then finding the documentation for it and being able to understand what's going on there so you can learn how to do it.
I'm seeing a little bit in the chat on the homework. We're going to talk about that in a few slides.
Yeah.
Yeah. Okay. Sorry, Aled, I think I cut you off there.
Yeah, basically just like one of the things we want you to get out of this is even though we're not teaching these domain-specific tools, we want you to, with the tools that we are teaching, we want you to be able to open up the documentation for those tools and learn how they work so that when you encounter a domain-specific tool, you can find its documentation, if it has any, and understand what's going on and hopefully learn it. So yeah.
Yeah. Also, no matter how far you get in like coding or research programming specifically, you are always going to be Googling stuff. I Google the most basic things still. That's totally fine. That's expected.
Yeah, I Google things all the time.
Okay.
Yeah.
Ada, do you want to talk about this one?
Yeah. So kind of dovetailing off of this, big ideas in this course is we want to teach you the fundamental, like the fundamental reasons why things work the way they do, more than we want to teach you how each individual thing works and exactly how to use it, because there are so many different tools and they go out of date all the time that, you know, we don't want what you learned in this course to become obsolete in 5-10 years, right? We want you to be able to continue to be able to apply that and learn new things. So by getting some idea of the fundamental ideas underlying how things work, you should be able to just, you know, in 20 minutes, hopefully go into a new code base in a language that you've never read before and start at least understanding what's going on and maybe modifying it a little bit. So one of our goals is that you should kind of have that intuition for how programming works. And yeah, so we want to separate this, like the details of, you know, like we want to separate the general case from the individual cases. The other thing we want to teach you about is abstraction barriers. That's kind of a weird term that some of you may not have heard before. So what is an abstraction barrier? Well, an abstraction barrier is basically like you define the way that one thing talks to another thing. So you have like, you define the way that a person drives a car with pedals and a steering wheel, right? And then if the way the car works completely changes, you know, you get an electric car, you can still drive that car. That's an example of an abstraction barrier, right? So one thing we're going to do in this class is we're going to give you functions that we want you to implement, and we're going to give you, you know, like a list of what arguments it takes, what arguments it should return, and how that mapping should occur, and then it'll be your job to implement that. And this is something that, at least from my experience working in other code bases, a lot of people who do scientific programming aren't that great at. It's kind of a lot of other code bases are like one big mush of stuff that is really hard to understand. So by just kind of getting in the habit of breaking down your code into bite-sized chunks and make A, your code a lot easier to read, and B, your code a lot easier to maintain. So if you're not copying and pasting, then if you have a bug, you only have to fix it in one place. So that's one of the things we want to kind of be into a little bit. And then the last thing I want to teach you is, like, how do the computers that you are working on actually work? And this might seem not very important because, you know, we have these high level languages like Python and stuff with libraries, but the things underlying how a computer does what it does bleed into a lot of languages in ways you might not really realize. So if you've ever worked with Python, right, you might notice that if you have a list and you pass that list to a function and that function changes the list, then if you access that list later outside the function, the change will carry over. But if you do the same thing with an integer, that doesn't happen. And that probably really confused you when you first learned it. And we're going to talk about the reasons why some of those weird things like that happen and explain why they're common to almost all programming languages. And by understanding those patterns, you can build yourself a better model of a better mental model of how the computer works and how you should program for it. And the other thing is, by teaching a little bit about how the computer works, hopefully they'll be able to write code that can be a lot faster. So like in the demo I'm doing, just by modifying my code a little bit and then applying some libraries, I was able to achieve a 30 times speed up because, you know, I knew what I needed to do to get that code to fit better into the model of how the machine works. And you're going to see some of this on the first homework in part 3, where you do stuff originally with loops and stuff, and then we move on to NumPy code where you operate on large matrices, right, all at once. And there's some special hardware in the computer that lets you do that, and it makes your life a lot easier, and it makes your code a lot faster. So we're going to talk about those types of things. I think that's the end of this slide.
Yeah. Before we move on, I feel we have thrown a lot of maybe new terminology at you right now, and we've talked about a lot of really big ideas. Let's pause for questions. So you can unmute yourself and say them, or you can put them in the chat. We're looking at both. We're looking at the chat. I mean,
interrupt us at any time throughout this whole lecture.
Yeah, you may not have been able to tell, but this is like very informal.
Yeah.
Like, it's a decal. It's not supposed to be like stressful or anything.
Yeah. So do we have any questions? Because there was a lot of things that I just threw out here. Apologize for that a little bit.
Okay. Seems like we're good right now, but again, feel free to interrupt us whenever. Okay, continuing. Now,
if you don't feel comfortable asking in like the chat, like totally feel free to DM us on Discord or something.
Yeah. Okay. So we've been talking and we haven't really introduced ourselves. So I'll go first. I'm Aditya. I'm a senior in engineering physics and engineering math and stats. Both of those are real majors that I'm actually in. I work with Professor Courtney Dressing in the astronomy department on exoplanet light curves and occurrence rates. You can ask me what those mean after, or in office hours or something. My CS experience is I had some basic high school CS, and I really got my experience taking 61A and 61B over here, or 61BL. And then I've taken some upper division courses in the electrical engineering department. A lot of my experiences come from teaching CS, actually. I'm the curriculum chair for ULab, and there I focus on intro-Python and stats and stuff like that. And there's actually little bits of content overlap between the work I do in ULab and the work over here. So for example, the Git lecture is going to be, I'm going to give the same lecture twice when we get to that. I've also been teaching at Berkeley for a while. I'm a TA for EX 126, which is a course on probability and random processes. And I've been a tutor in math at the SLC for about 3 years. And my fun fact is my middle name is actually from Lord of the Rings. It's Rohan, which is an actual like Indian name, which is exactly how my dad got away with it. Like his first purchase with his own money was the set of Lord of the Rings. So he was just absolutely thrilled to, have the opportunity to do this to me. and I'm here for it. So.
Hi, I'm Alid. I'm a junior physics major. Most of my research on campus happens with Professor Yuri Kolomensky and Dr. Yame. And some of you might have had Yuri. He teaches Physics 77 and Physics 88 pretty regularly. My CS experience is a little bit more informal. I've programmed for a long time, and I've taken the 61 series. And I also have a lot of experience working at the low level with computers, partially just because I find it fun. So I've done some work actually designing like integrated circuits in a couple different places. So if you have questions about, I find that stuff really cool. So if you ever have questions about that, feel free to at me on Discord. And I can talk for hours about that type of thing. Unlike Aditya, I've never taught anything before. So the first half of this semester is going to be an adventure for both of us. So hopefully you'll enjoy that. And I was told to put a fun fact. I can play cornet really badly. It's like not, cornet is like it's basically a trumpet. Yeah, I don't get to practice very much because my apartment mates stop me. So, but maybe we might hear some at the end of this course. Who knows? Probably not for more than a minute. Yeah.
Everyone has to demand that Al does this now in like a Ross lecture or something.
Yeah, I don't know how well the high-pitched squeaking is gonna manage through Zoom's audio compression, but we'll see.
Okay.
Yeah.
I was going to suggest that everyone go around and introduce themselves, but in a very happy turn of events, I think we have too many people to actually do that. So we'll do that if we have time at the end. Otherwise, chat on Discord or meet in office hours and that kind of thing.
Yes.
Okay.
We'd love to get to know all of you. One thing I would like to say is, even if you don't want to introduce yourself on like Discord or something, please fill out the form survey we posted. That lets us know, like, for me, the most important part that lets me know is what type of computer you have, so that I can make sure that all of my assignments, which are a little bit more low level, actually work on everyone's computer, which may be a little bit of a struggle. So please fill that survey out as soon as you get the chance.
Yeah. Okay, so here's the overview of the course. So we're basically dividing this into 4 parts. This is the introduction. Today are just going over everything logistically and like what we're trying to achieve. And next week, where Alid talks about, what are the tools you should be comfortable with going in. And we've got a homework associated with that where you do some setup, you do a little bit of Python review, and we introduce you to our first like big scientific computing idea, Monte Carlo simulation, which you might have seen if you've taken 77 or something similar. So after that, we're going to go into 4 weeks of computer architecture. Alid, talk a little bit about what you're trying to achieve there.
Yeah, so we're going to hopefully talk about a very high level model of CPU, and hopefully talking about a very simplified processor will help make a lot of things make sense. So like, why is NumPy way faster than the code that I write in Python that does the same thing? Or like, why are lists passed by reference and integers not? Like, so we're going to talk a little bit about that. And then after that, we're going to talk about writing parallel code, which is really hard. So we're going to talk about it in a simple way, and then talk about why things sometimes don't work. One thing I would like to note about parallelism, it's hard. Don't feel bad if you have trouble with it. Everyone has trouble with it. And I think there have been more than one paper that's been retracted because someone had a bug in their parallel code and it threw the results all off. So yeah. And then we're going to talk a bit about accelerators. So we're going to talk about GPUs, and then maybe talk a little bit about FPGAs, which is where I kind of personally think the world of supercomputers is going to go in the next 20 years, but we'll see. And then after that, Aditya is going to talk a little bit about more scientific computing stuff.
Right. So Alan's taking like the very low level. I'm taking the opposite. I'm taking the high level of if you've written something, how do you know that it's efficient? So we're going to talk about asymptotic analysis, which is how computer scientists like figure out, okay, this code runs well in theory. This doesn't. Can we figure out like better ways to write our programs? We've already gotten all the mileage we can out of like optimizing the computer. Let's optimize the steps. And then we're going to start applying these tools to actual science problems. We're going to talk about like numerical methods of simulating things. We're going to talk about probabilistic programming. I heard someone at the start mention they want to look into machine learning. We might do a bit of that as well. So this bit's more like customizable to what are your like science interests. And hopefully by this point, like half, 2/3 of the way through the semester, we'll have discovered like discussed like the kinds of science y'all are interested in, and we can start looking at those applications and like how do those work in the real world. And a really good benchmark at the end of this is if you're able to do something that like probably a lot of research groups will ask you to do, take a scientific paper and replicate whatever method they have for their analysis, like MCMC or simulation or something like that. And we'll talk about what MCMC is. You'll actually discover it in this first homework. And then after that, we've got 4 weeks of you doing a project, which is basically just anything that's interesting to you. And we're going to be doing lectures on like stuff like documentation that's going to be useful as you do that.
Yeah. We also might do some lectures on some weird topics. And if you guys have like near the end, if you have specific things that you want us to lecture on that we think we might be able to lecture on, let us know. Like we might do some DSP, which is digital signal processing. So like that's kind of what I do a lot of at LBL. But yeah, whatever you guys want to do.
And probabilistic programming, which I talked about before, which is just the idea of like, you know, like at its basic level, it's like what parameters to a model explain this data really well, and like all those like subtleties and added layers of complexity you can put on top of that. Okay, next up, CS ultimately needs practice. We're going to try to make this like low stress and as easy as possible, but ultimately the only way to like learn these things is to do them. So we're going to try to be as accommodating as we can about this. So we'll be like pretty relaxed about deadlines and that kind of thing. But the thing that I don't think other classes really do here is a homework time budget policy. So you should be taking this class for 2 units, and we'll talk about that in a minute as well, which means 6 hours a week. So just knock 1 hour off just for Slack. So that's 5 hours. 1 of those is here in lecture. 4 of those should be on homework. And we'll be releasing the homeworks like 1 every 2 weeks, and there's 5 of them, and the rest of the class is on projects. If you take more than that time, you can just explain like what you've done, what you would want to do next, what's easy, what's difficult. Just write a few lines about that to us, and you'll still get full credit. We don't want you taking like insane amounts of time on a decal, but we also want to enforce like, you do have to put in like enough work that you get something out of it. And of course, you could cheat this and just like not really try and just turn it in saying, oh, I tried for the full allotted time for this homework. But, you won't get as much out of it. It's not fun for us. So we're just going to trust this works on the honor system. Just actually try, and we'll be here to help you throughout.
Yeah. The one exception to this is, of course, you need to do part 1 of this homework all the way through. You need to set up your programming environment so you can do all the rest of the homeworks. I don't think we have a time budget for that, but if you do have trouble with it, tell us, and we have both, I think, have fairly flexible schedules. So or also with the other homeworks, if our office hours don't work for you, we can probably find another time that does.
Yeah, we're like I said, we're on Discord quite a lot because like we have other things there usually. So you can feel free to message us and count on a decently quick response. But the idea is this isn't meant to be stressful, but it is meant to be sure that, you know, you're learning what you signed up for. Okay. Right, here's some logistics. If you're not on the Discord already, I think most people are right now. Please do that, and please fill out the survey. I put the link in the chat way before. Let me just do that again real quick. Whoop, can I copy? I can't copy. There we go. So there's the form.
Does anyone here need? Does anyone here need the Discord join link? Okay, I'm gonna post it anyways.
Yeah, I did that. So okay, so Discord join link. Alex is gonna put that in the chat. Okay. Also, this is a 2-unit class. I've seen apparently the department like made a mistake while they were setting up this course, and they let you pick anything from 1 to 4 units. So we're fine with people taking it for 1 unit. Only you should expect 2 units of work. Like some people have talked to me about like they don't want to hit the unit cap and go through administration just for a decal. That's fine. Just like expect 2 units of work. And if there is enough demand for it, we could also just say there is a scale back 1 unit version where you just do the homeworks and not the project. And that works out to the same time budget. But, you know, we'd rather not do that. Just, you know, we're trying to be as flexible as possible so you guys still learn. Okay. Our regular office hours are Wednesday 7 to 8. That is going to be Alad's office hours. Mine are not set. I have like pretty flexible availability. Sorry, I'm just gonna, I didn't copy this link before, so I'm gonna.
We'll post the slides afterwards.
Yeah, but I also just wanted it in the chat right now, just for the sake of having everything in one place. Yeah. So fill that out to set when my office hours should be, and you know when you can come talk to me. Okay. Homework 1, we released it this afternoon. It's the link is on the chat, is on the Discord under assignments, and it's in 3 parts. The first part is environment setup, which technically has a budget of 4 hours, but you know should take way less than that.
Yeah, it should not take very.
Yeah, it's just.
Sorry if I scared you with my thing. It will probably take like 20 minutes, but
yeah, we're trying to like way undershoot the time budgets for the first homework at least. Just you know ease into it a little bit. The second part's a coding basics review where you don't need to like solve anything. It's just run through and understand the whole notebook we put together, and that should take 1 hour if you've seen these things before, but maybe you're a little rusty. And part 3 is Monte Carlo simulation, which is designed for 3 hours, but again should take way less. We're hoping. But you know, if we end up way overshooting, let us know, and you don't have to work on it more than the time you signed up to work on it. Also, a little subtlety is in our syllabus right now, it says we're doing homework 1 this week and homework 2 next week. We just changed that around a little bit and merged them both into a common homework 1 so that every homework's weighted equal and you don't accidentally waste your drop on a really easy homework.
Yeah. A quick thing, the 2 things that are not mentioned here. Homeworks are going to be posted on the website, which I'm assuming you all probably have the link for, but we'll post in Discord and pin it just in case.
Yeah, it's just PhysCatDecal.com. There. Whoop, sorry, cut you off there.
Yeah, there's an ad. The other thing is submissions will happen on Gradescope.
Yeah, everyone should be on the Gradescope, but let me know if you're not, because I'm doing this manually because I was too lazy to set up a B courses and now I'm paying the price. But let me know if you're not on the Gradescope and I will add you manually. Okay. Yeah. Final projects. I'm going to try and breeze through this to give Alad a little bit of time. This is what we're going to be doing for the last month of the class. It's basically, do anything programming related that you want to. If you're already doing something for another club or research or class, as long as like the person in charge of that is okay with it, you can use that as your final project here as well. All we're going to require is, it has programming in it. It uses something you learned in the class. It uses version control, which are like the kinds of requirements you would have for writing anything anywhere. If you're writing like a package for research or something like that. Okay, Anna, you cover this, and then I think it's your part.
Yeah. Yes. So we're going to be using Anaconda for the first half of this class, at least, to manage basically everything we do in Python, which is a lot of this class. if you've used Anaconda before, you might have found it unpleasant. I agree. I'm sorry, but it's the best way to do this in a way that's cross-platform, so that we support Windows, Mac, and Linux. It's better than Docker, so we've got that going for us. Yeah, so we're going to be using Anaconda. In the environment setup, I noted a couple ways you can install Anaconda if you're comfortable with the command line that are a little bit less heavy than the default installation. The other thing is you'll probably want to know how to open a terminal or a command prompt and perform basic operations inside. So listing files in directory, moving between directories. We'll have a tutorial on this, but I know it seems like a really steep learning curve, but it's not that hard. And when you do research, most things don't have GUIs. It's something you're kind of just going to have to get used to. So yeah, and this is going to be necessary for the portion of the course where we talk about Git. We're going to try to make sure to the best of our ability that there is instructions for everything that's hard on the website. So the instructions for the environment setup are already posted. If there's something that doesn't make sense, please tell me, because I promise you're not the only person who's confused, and I will give you an explanation, and then I will add information to the website. So actually, it's the next Monday's review session. That's a typo. The review session on Wednesday will be focused primarily on making sure everyone's up to speed on environment setup and stuff. I highly recommend you come, and at least try to get everything installed before then. It won't take that long, and we'll both be available over Discord. So yeah.
And now,
this is where I show something sparkly to hook you into this course. So I'm going to try to share my screen, and Zoom is probably going to yell at me because it usually does. Okay. Is this sharing?
This is sharing. We're seeing your
Is it
Discord.
sharing?
Yeah,
Awesome.
it's sharing, but it's sharing everything. Okay.
You need to invite Rajiv.
Is it sharing my Chrome window now?
Yeah. We see the slides.
There's also slight inception on Zoom.
Okay. Sorry about that.
Oh, there is a bit of a Zoomception, yes. Oh, that's just me.
Small Aditya, is there less Zoomception? Okay.
Yeah, but maybe don't like. Yes, we see the notebook.
Okay. Is that all you're seeing, or is there a bunch of other stuff?
That's all we're seeing. It's fine.
Okay, awesome. So one of the things I wrote, and one of the things that we'll be talking about in homework 2, is we're going to continue this idea of using Monte Carlo techniques, and I kind of want to emphasize the scientific applications when we talk about low-level stuff. So one of the things I wrote is a ray tracer. I don't know how many of you know what a ray tracer is, but a ray tracer, basically, you try to physically model how light interacts with surfaces to render a scene. Instead of kind of the more geometric, you take some triangles and you figure out what transforms them visible on a screen in a way that looks 3D. And ray tracing is a lot of fun. It's a way a lot of rendering in, like, for movies and stuff happens. It's also very computationally sensitive. And the thing that makes it interesting for us is that it's fundamentally a random process, because, for example, if you scatter light off of a wall, you're going to get light going in random directions. So it's a perfect application for Monte Carlo simulation, where you want to try to figure out what the average color of, say, a wall is. So I wrote a ray tracer, and we're going to be touching on it in homework, in the first homework. Now, one of the things that, of course, you can write a ray tracer in any language in any course. So why? Second homework. So why should you, take this class, right? Because it's not about ray tracers. This class is about science. It's not about ray tracers. One of the things I did is I used a tool called Numba, which is a tool for compiling Python. And that's what one of the things I'm going to talk about in my architecture class. So if you don't know what compiling is, most like Python as a language is interpreted. So someone wrote a program for the computer that reads Python code and runs through it, kind of the same way you would if you were staring at the code and running through it in your head. A compiled language is a language where you take your code in, say, C or Python, and then you transform that directly into the representation that the machine understands. And that's a lot faster. So when I had this ray tracer written originally in just population, it took 40 seconds to render a 100 by 100 image, 100 pixels by 100 pixels. Now, that's not very much, very grainy. By applying these compilation techniques and being smart about how I laid out the functions, and it took a lot of refactoring to do this, which is one of the things I'm going to teach you, is how do you write Python code that can actually compile. I managed to speed that up to about 2.5 seconds for a 100 by 100 image. So I wrote this ray tracer, right? One of the things I tried to do to give to kind of be a good example is I broke the ray tracer into a bunch of different parts. So we have a function that you have a ray and it comes out of the camera and it just advances it forward until you hit an object. You have another function that when it hits an object computes how it should bounce. Is this a mirror where it bounces in the way that the angle of incidence is equal to the angle of reflection, right? Or is it a wall where it bounces in some random direction? And then I took those two functions and I composed them with functions that describe, different shapes, like a square or a plane or a sphere, right? And you're going to be writing some of those, so I'm going to scroll past those real quick. And then I tried to write a function that describes some small world. So you're in a room that's a box and you've got a plane of light overhead and you've got a sphere that's a mirror in the center. And one of the things I tried to do is I wrote some functions to compose multiple objects. So, for example, we have a box here, but when you make a room, you don't want a solid box that is like a cube. You want basically a solid world with a box subtracted from it. So I wrote a function carve, which takes a box and subtracts it from the world, right? So you do all this, and instead of it taking, hours and hours for you to generate a small scene, you can now do it pretty fast. So I'm running it, and to run a lot of this class is going to be in Python notebooks. So you hit Control-Enter to run. So I'm running this, and this star means it's currently running. Now, one of the things about compilation is the first time you compile something, it takes a little bit longer to run. That's because there has to be other software in there that transforms this representation here into a machine code representation, right? And that's fairly computationally intensive. But then we can render that image. And you'll see we have a box, we have a sphere that's a mirror in the center. And being able to do that in a few seconds has two advantages. One, you can render larger scenes, but two, if you have some program you're working on and it takes 10 minutes for you to run to run it, and you're trying to debug your program, that's like, if there's an error, that's, you have to wait 10 minutes to see if you fixed it. Now you've only got to wait a couple seconds, which is a lot better. So we're going to be going through this ray tracer in detail, but some other interesting things that I want to touch on is by defining interface to these shapes. So what these shapes do is they take a position and they return a distance. They take a position, they return the distance of that position to the closest point on that object, right? And by defining that interface between how the shapes work and how the ray tracer works, I can make quick changes to this. So for example, right here, we have a sphere in the center of the screen, right? Say I want a plane, a mirror, right, that is just above the bottom of the scene. I can do that. I can, what's the function? I can make a union.
Yeah, Alan, in the chat, your audio is a little unstable. Yeah. It's sort of cutting out. Maybe you should switch off your camera and see if that makes it any better.
Yes, Zoom, hold on. All right, am I slightly more stable now?
Let's hope.
Okay, yeah, so I can use this function union maker that I wrote that to make a union between that mirrored sphere and a plane that takes up the bottom half of the screen. So based on how the plane maker function is implemented, that's carve plane maker, and it's going to be at height 0.5, right? And I've now created this new object, and that was pretty easy because of the abstraction barrier that I defined, that describes how these shape functions get called and what they return. And I can regenerate the world, and it gets mad at me. Wild crap. Okay, I can replace here. Sorry about that. This is still a little bit beta. This is what I get for trying to do a live demo.
Number one law of programming, it will only work when no one else is looking.
Yeah. So I'm just going to make a, wait, hold on. It looks like there's an issue with carve, so. I'm gonna make a, that doesn't work either. Okay, this was a bad idea. I'm horrible at live demos. Please ignore all of this. I'll have this bug worked out before we do the homework. No, still not happy.
How about you just go with what you had before, but change the parameters a bit?
That's a brilliant idea, Ditya.
Just go with like, it was what, sphere maker 3.0, change the 3.0 to something else. Don't worry about carve. Like just the idea.
I co-lecture because I get very, very tunnel vision sometimes. So the 3.0 is the radius, and the 15.15.8 is XYZ center position. So by changing this to a 1.0, we can have a little sphere, and it'll run, and it's got to recompile because I changed stuff, and the compiler is a little bit dumb, but that's what you get for trying to compile Python. And it doesn't take that long. And we've got a new image with a really small reflective sphere, or we can make it much bigger, right? Or we can even, so we can make it like 4.0, and we can intersect it with the ground, right? And this still works because we have done our best to be aware of all of the abstraction barriers, right? So for example, this is a sphere intersecting with the ground and it still works. And yeah, we're out of time. I just wanted to show you something quick that I rendered earlier, which took about 5 minutes. A 300 by 300 image where we cast 128. So right now we're casting 16 light rays for every pixel. So I rendered a 300 by 300 image where I cast 128 for every pixel. And it took about 5 minutes. If I had done this with the pure Python implementation, it would have taken over an hour. I tried. It ran for way more than an hour and never finished. And just by changing a couple parameters, you can make a really high res rendered image. And one of the things I'm going to try to do for you is document how all of this works. And then you can go off and have some fun and play with this and hopefully create something that looks really neat. That's the goal. So yeah, that's all I've got. I apologize for the hiccup during the demo. I hope this was a little bit interesting and maybe hooked you a little bit for this course, because you're gonna get to play with this on not next Monday, but the Monday after. So yeah.
All right, that's all we've got for today. Thanks everyone for coming, and we'll see you in office hours on Wednesday and lecture next Monday.